Hello, we're going to look at a lesson today that's more about what most people probably remember about Algebra 1, and that's solving equations. I want to point out to you that the name of this lesson has two words in it that I kind of want to talk about real quick. Easier as in relatively easier. The next lesson will be about solving harder problems. And so these are ones that are mostly review. You mostly remember how to do these problems already. And then each of these equations is going to be linear, which you may or may not remember what that means from Algebra 1. I will get into that in the lesson. Students will be able to say that they can use inverse operations to solve 1- and 2-step equations. A couple of the last examples will use a few more than 2 steps, but we're just sort of getting there. And then, what would those extra steps be? Well, they could be combining like terms, using the distributive property, or there might be variables on both sides. So we'll start with an introduction and sort of brief history. What is algebra? Algebra is concerned with structures and relationships. And you know you're doing algebra when you see variables. It's kind of the shortcut, cheater way to know the difference between arithmetic and algebra. Just like you know you're doing geometry when you see shapes. It's not 100% accurate, but it's a good way to know the difference. You know you're doing algebra when you see variables like x. The basic idea of algebra does go back to ancient times, including Babylon and Egypt. But Diophantus, who was an Alexandrian Greek, he somewhat gets credit for being one of the fathers of algebra. He lived approximately 1,800 years ago. But the word algebra is not a Greek word. It is an Arabic word. In Arabic, it refers to something like the idea of restoration or setting broken bones. And the word algebra actually comes from the title of a book by, and this is, of course, is an artist's rendering of what he would have looked like. And I don't speak Arabic, so I may be butchering this. Al-Khwarizmi, who was a Persian or Arabic mathematician. He actually lived in what you and I would call Baghdad about 1,200 years ago. And so keep in mind sort of what was going on in the world. After the Greeks were the most powerful civilization in the Mediterranean, it was the Romans. And then when the Romans fell, that's sometimes referred to as the Dark Ages in Europe. There wasn't a lot going on in Europe in terms of progress. That was actually sort of a great time to be living in the Middle East in terms of scientific progress. It was their golden age. And so a lot of these important Greek ideas had actually spread into the Middle East, and then some were lost in Europe, and they were preserved by Arabs, and then they got spread back into the Middle East right around the same time as, like, just before the Renaissance. In fact, you could argue that's what helped get the Renaissance kick-started, was ideas spreading from the Middle East back into Europe. Algebra takes on what you and I would call algebra and look at and think of as algebra from around the mid-1500s to mid-1800s. The European mathematicians have a chance to sort of reabsorb all this tradition and legacy, and they started creating their own symbols that we now use. So a lot of people think of algebra as sort of symbolic manipulation of things. That is actually more recent. Diophantus and Al-Khwarizmi would have worked with things more written out, like a thing and 3 is 5 would have been their x plus 3 equals 5, so to speak. Alright, so let's jump right in. Here are the algebraic properties of equality, and a, b, and c are real numbers. The idea is that if you know two things are equal and you add the same thing to both sides, or subtract the same things on both sides, or multiply the same thing on both sides, it is still equal. The one catch is that when you do a division, you must be sure that you're not dividing by 0, because division by 0 is undefined. And so those are our 4 algebraic properties of equality, and they're sort of the gears of algebra that let you get work done. You'll hear me say a lot about inverse operations. Inverse operations cancel or undo, and they occur in pairs. And so here are the 3 common pairs. This lesson we won't use exponents or radicals any. That'll be later in the year. But we've done order of operations, and we've mentioned exponents and radicals, so I thought I would kind of throw it out there. Okay, the good old socks and shoes rule. If a process must be done in a certain order, then reversing the process, reversing the order reverses the process. To do something in one order, you then can undo it in the opposite order. The process is done in a certain order, and then you reverse the process, reverse the order. You can undo things. So why is it called the socks and shoes rule? Well, in the morning you would put socks on, then shoes on. In the evening, when you're done wearing socks and shoes, you can't take the socks back off first. You have to take the shoes off first, then the socks. So that's why I often refer to it as the socks and shoes rule. And that's not just a me thing. There are other people who would know what you're talking about. Not necessarily everyone, but there are some. So here we go, order of operations. Leaving out grouping symbols for the moment, just thinking about the actual true operations. You got exponents and radicals, multiplication, division, addition, subtraction. Each of these lines is a pair of inverse operations. When you're doing arithmetic in red, you start at the top and work your way down. And that's how you evaluate an algebraic expression. You start at the top, work your way down, doing things. Well, algebra is all about undoing. So you would actually start at the bottom and work your way up, generally speaking, to undo things. Well, what are we going to be working on? What are we going to be undoing? Well, we're going to be undoing or solving linear equations in this lesson. And a linear equation is any equation that has this form, ax plus b equals 0, where a and b are real numbers, a is not 0. The solution of that equation is a value of the variable x that makes the equation a true statement. For the general abstract version, ax plus b equals 0, hopefully you can convince yourself that the solution is the opposite of b over a. Now, not every equation we solve is going to look like this. They're going to look a lot of different ways. The point is we can make any equation we're going to solve that's a linear equation look like this. And that idea is called equivalent equations. Equivalent equations have the same solution, and they can be transformed into each other using algebraic and arithmetic processes. So a real straightforward, or relatively straightforward at least, example, is some of you might not like the fraction too much, is that each of these equations is equivalent. And then the idea is, how do you transform this equation into this equation? Well, a lot of you are probably remembering that you've subtracted 1 on both sides. And then how do you transform this equation into this equation? Well, with a little bit of looking at it, hopefully you realize you've multiplied by 5 on both sides. And that would leave you with 3x is equal to 30. Well, then you would divide on both sides to transform this equation into x equals 10. And that's sort of the big idea. That's all the notes, so to speak. The rest is examples. And so here we go. Now here's what we're going to do. We're going to solve these, but we're going to also talk about how we solve them, which is what's going to bother some of you all. And so what I want to do is, like this first problem, we would add 6 on both sides, and we would get that x, well, negative 9 plus 6 would still be negative 3. And some of you might remember showing little like plus 6, little plus 6, and you draw the line and you write x equals negative 3. And I'm not going to try to break you of that. I call that showing the bookkeeping. If you want to show the bookkeeping, go for it. But what I have to see in terms of work is honestly just that progression of steps from here to this equation, to this equation, to this equation. And at each step, you're doing one logical transformation to get an equivalent equation. And so what we might do for purposes of this lesson is we would write our next step, and then sort of in between them, we would write something that tells us how we transformed. And so you added 6, so you could write add 6, which a lot of people just do plus 6, but we're not going to do it that way. We're going to use the words. So we're going to write addition and then show what we did. So this next problem, we would add 3. So addition. Well, when you add 3 on both sides, you're left with the opposite of x is 7 plus 3 makes 10. The positive 3 cancels the negative 3 to a 0, and you're left with negative x over here, or opposite of x over here. And then 7 plus 3 makes 10. Well, then one way to move this negative to the other side is to multiply. Ooh, that P didn't come out. Pretend that says multiplication. So you do negative 1 times negative x, and again, you don't have to show that for me as long as you show me the steps. Would cancel to positive 1 or positive 1x. And so we would have x is negative 10. Okay, well, how would we cancel this addition? What's the inverse of addition? Subtraction. So we would subtract 1.2 on both sides. So we're going to write subtraction. Let's say the pen there for a second wasn't wanting to pick up. Subtraction. And when you do 3.1 minus 1.2, a lot of you might have a little trouble with that unless you think of it as money. So think of it as $3.10, and you spend $1.20. How much money would you have left? Well, you would still have the 10 cents, and then the $3. You're spending $1.20 out of that, so you might go, well, that's $1.80, or that's 80 cents away from 2, and then 2's $1 away from 3. However you want to think about it, you end up with 1.9. 1.9. So x equals 1.9. That's, let me just put the decimal point back in. That's the number that we could add to 1.2 and get 3.1. That kind of gets me back to what I want to say real quick on these first 3, going back to sort of that idea of solutions. This is the solution because when you put it in the problem, it checks. Negative 3 minus 6 equals negative 9. It makes the equation a true statement. It's not the solution because you solved the problem and that's the number you got, because that number could be wrong. So kind of keep that in mind. Alright, so here's another one that's kind of more of a one step or not very many steps to get an answer type problem. X divided by 2 is 8. Some of you might be able to just look at that and know that the answer is 16. I know it's 16. 16 divided by 2 is 8. But if you're having a little trouble with it, you might say, well, how would you get rid of or cancel or undo a division by 2? Well, you would do a multiplication. So you multiply by 2. Again, pretend that says multiplication. Apparently, pen doesn't like me very much on multiplication. So you multiply by 2 on both sides. These 2's would cancel to 1. So you'd have 1x or 1. And then 8 times 2 is 16. Alright, well, how about this problem? What operation can we use to undo this multiplication by negative 3? Well, we could divide by negative 3. So this one is a division. And so when you divide negative 3 by negative 3, divide a number by itself that's not 0, you do get 1, or 1x over here, and then 1 over negative 3, or negative 1/3. Okay? This is a problem that is considered to be a basic Algebra 1 type problem, but the fact that it's a fraction times x, might really bother some of you. So if you have a lot of trouble with this, I recommend solving it in 2 pieces. Get rid of the division part of the fraction first. That's what you dislike. And to get rid of division, you would multiply. and that says multiplication. So you multiply by 7 on both sides. It cancels out the denominator, and you're left with 5x is equal to 10 times 7 is 70. Well, now we want x by itself, so 5 times x is 70, so we've got to get rid of a multiplication by 5, so we divide. So now we're going to do a division. Hopefully your notes will be a little neater than mine. And so x is going to be 70 divided by 5. Well, 5 times 10 is 50. And this is 20 more. And 5 goes into 24 times. So that's a 10 and a 4 or a 14. So x here is 14. Let's check that real quick. 5/7 of 14 should be 10. Well, how many times does 7 go into 14? 2, and then 5 times 2 is 10. So our answer does check. You should have checked every once in a while just to make sure you're doing it correctly. Alright, so what would we do first on this is now a two-step equation. It's now a two-step equation. Well, we get rid of additions and subtractions before we get rid of a multiplication or a division. So we would cancel this addition by 3 first. And so we're going to start by doing a subtraction. For these words, maybe going completely in cursive is the way to go. Well, if you subtract 3 on both sides, plus 3 minus 3 cancels out to 0. All that's left here is 4x. And then 11 minus 3 is 8. Well, then we want to cancel this multiplication by 4, so we do a division. And 4 divided by 4 is 1 or 1x. And 8 divided by 4 is 2. And so we could quick check and say 4 times 2 is 8. 8 plus 3 is 11. This one starts the same. We're still going to subtract by 3. Still going to subtract 3. This time we would get 2/7 k equals 6. On these last few, I throw in a few instances of other variables. Even though x is the most common variable, I don't want you to think the variable has to always be x, or that I'll always use just x's. By the way, the variable always being x, that actually also goes back to the fact that this comes out of Arabic, and I will show you a video on that in class. So, 2 different ways to finish this problem. I've already shown you one way. You multiply by 7 to cancel the denominator. I'm not going to write the steps because I'm going to show you 2 different ways. So I'm going to do it from there. I'm going to finish the problem 2 different ways. 6 times 7 is 42. That's a multiplication that most people don't like a whole lot. And then to cancel this multiplication by 2, we divide by 2, and you get 21. Now, a different way to do this, if you're really comfortable with fractions, and some of you might already know this, let me show you the different way in purple. A different way to do this is to say, okay, I'm going to start with 2/7 k is 6. Okay, if you really are really comfortable with fractions, here's a way you can do this differently. What do we do to solve this problem the other way? We multiply by 7, then divided by 2. Well, that's really just, the reason why that works is you're taking the reciprocal of this fraction and you're multiplying by it. So that you multiply by 7 and divide by 2 all at once. And what happens when you do it that way is that the 7 halves and the 2/7 would multiply together and cancel to 1, leaving just k. And then to multiply this, you can think about the 6 as being over 1 if you need to. And you either do 7 times 6 is 42, 42 over 2 is 21, or I would cancel first and say 2 and the 6 is 3, 7 times 3 is 21. I do not care which of those 2 ways you finish this problem. I don't care whether you do it in 2 steps, and multiply by 7, then divide by 2, or if you do that all at once using a multiplication by 7/2. Whichever way makes more sense to you, please use. Okay. Alright, now we've got about 4 examples left, I think it is, and you might be noticing they're getting a little tougher. So what about if we have a fraction on one side equal to a number, and then the numerator of the fraction over here is a little tricky looking? Well, the part that's bothering you about this problem, if you don't like the way it looks, is the division by 5. And what gets rid of a division? A multiplication. So we're going to multiply both sides by 5, and the 5's will cancel to 1, leaving 2p minus 3. And 5 times 7 is 35. This equation is equivalent to that one, but I think you would agree that this one looks much simpler to solve. We do an addition to cancel the minus 3, to cancel the subtraction by 3. So if you add 3 on both sides, you would have 2p is 38. Well, to cancel multiplication by 2, we need a division. P is, well, half of 40 is 20, so half of 38 would be 19. Alright, so here we go. Ooh, what's going on in this problem? What's these parentheses? Can we do that first? No, there's nothing in there we can do first. Oh, wait a minute, we got this 3 outside the parentheses. And so the first thing that we probably should do on this problem is distribute. So I'm going to write distributive or distribute. I'll take either one. For those of you that are a little lazy, I'll take multiply, add, divide, subtract instead of writing out the full name. Those are acceptable shorter versions. You're going with the verb instead of the see, what I'm emphasizing here is that we're in fact using all these properties that we've talked about. Well, this would be 3 times x is 3x. 3 times 1 is 3, so minus 3 plus 2 is 5. I personally at this point would then combine like terms. Negative 3 plus 2 is going to be negative 1. So 3x minus 1 is 5. And you can either write combine like terms or simplify. I'll take either one. If I were writing it on paper, I'd probably write combine like terms, but since it takes a little more effort to write with this electronic pen, I'll just write simplify. Well, now we need to cancel this subtraction by 1 using socks and shoes or inverse operations, those ideas. So we're going to cancel that subtraction. We'll do an addition and get that 3x is 6. Well, that's 3 times x is 6, so now we need to do a division to cancel that. And so when you divide both sides by 3, you get 1x, or x, is 6 divided by 3 makes 2. And so what this equation ended up being was a 1, 2, 3, 4-step equation. The idea is that these words we've been writing out to the right-hand side are actually describing what we're doing at each step. And so you go back and look. 1 step, 1 step, 1 step, 1 step. We did 2 on this one. We did 2 on this one. 2 on this one. We did this one as a 3-step. And I just didn't write in the reasons because I wanted to leave space to show you the 2 different ways. Okay. So we got 2 examples left. Uh-oh. These 2 both have variables on both sides. And generally speaking, variables on both sides, I want to get rid of that as soon as I can. So I'm going to actually start this problem by consolidating the x's so that there are not x's on both sides. And I usually want to do this in such a way to either do one of 2 things. I either want to keep my variable on the left, just because that's what most students are more comfortable with. But I will overrule that at any point if moving it to the left creates negatives or keeps negatives coefficients on x. but moving it to the right would create positive instead. Because as much as students want that variable to be on left, I feel like they make more mistakes if they prefer that to avoiding the negative. So here we go. We want to get our x's together, so we're going to take this x and we're going to subtract an x on both sides, and that will keep this balanced. One way to think of all this algebra stuff, let's see, let's do this on a separate new sheet. One way to think of all this algebra stuff is that you have a balance or a two-pan scale. Oops, jumped a little bit from the door. Let me get that. Okay, I'm back. And the idea, I went ahead and finished the drawing before I pressed record, is that algebra is all about balance in some ways. And so I have kind of a two-pan scale here. On the left-hand side, there are two unknown values and three values that I know are 1. And so that would be like 2x plus 3. And I've balanced that on the other side with 7 ones. And so 2x plus 3 equals 7. But if you start canceling things off of both sides, you know, the 3 ones would cancel these 3 ones, and then the idea is you got 4 things over here, and so you can group, because you've got 2 x's over here, you would have 2 groups. So that means that each x would have to be the same thing as 2 ones. Well, that's just like solving this equation. You subtract the 3 off, you get that 2x is 7 minus 3 makes 4. And then you take the 4 that are left and you group it into 2's, because that's how many x's you had. And you get that x is 2. And so the idea is that equation is like a balance. It's got to be equal because the equation says so. So we're going to subtract an x on both sides. 3x minus x is 2x. So 2x minus 5 is, this x is canceled to 0. 0 plus 7 is 7. 2x minus 5 is 7. So we did a subtraction by x. I'd even write that maybe, since so many of you might think of by a number. Then we're going to add 5. Well, you add 5, it cancels the negative 5, the minus 5 to 0. 2x plus 0 is still 2x. And 7 plus 5 is 12. Well, how do we get rid of this 2x? We just want x by itself. So we're going to undo the multiplication and do a division. And you divide 2x by 2, you get just x, or 1x. And 12 divided by 2 is 6. And so now we can check this. 3 times 6 is 18. 18 minus 5 is 13. Well, 6 plus 7 is also 13. So it is a true statement when x is 6. You look this problem over, you might say, well, okay, what are we going to do? Lots of things going on here. There are a couple different things you could do first. I'm going to start with distributing the 3. Not what you had to do first, but it's what I'm going to choose to do first. So I'm going to distribute the 3. You get 8x plus 3 times 1 is 3. 3 times the opposite of x, or 3 times a negative x, would be minus 3x. You can think of there as being a 1 right there if you like. And then this side I didn't distribute, so it's still just 7 plus 4x minus 1. That might be the part of this that some of you don't like, is since I'm writing down each reason of what I'm doing, you can only really do one thing at a time. So now we're going to do combine some like terms, or simplify the problem. Well, on the left hand side, 8x minus 3x you have 8 of something, you take 3 away, leave 5, so it's 5x plus 3 equals. On the right hand side we have a 7 and a minus 1 that can be combined. Well, 7 minus 1 is 6, so it would be 4x plus 6. From there it works very similar to this problem. We're going to subtract, let's see, 5x and 4x. We're going to subtract 4x on both sides. To get x plus 3 is equal to 6. Hey, that lets us subtract again, this time with the number 3. And if you subtract 3 on both sides, this will just be x. X plus 0, but you don't need the plus 0. X is 6 minus 3 is 3. So we can go back to the original problem, and you'll have to substitute 3 in for each of these x's. So let's actually start over here on the right hand side. 4 times 3 is 12. 7 plus 12 is 19. 19 minus 1 is 18. Put a 3 in here and here. So 3 and a 3. So we start in the parentheses. 1 minus 3 is negative 2. 3 times negative 2 is negative 6. 8 times 3 is 24. 24 plus negative 6 does make 18. So it checks. It is a true statement when you get 3 on both sides. Alright, so that's it for solving easier linear equations. Let's see how hard I can make them in the next lesson. See you next time. See you in class. Good luck.